Okay, think about the last time you stood on a bathroom scale, maybe at the doctor's office. Why did it tell you to stand still? Probably because it didn't want the reading to fluctuate. Because if you move, then it kind of goes up and down in a weird way. Is it can you predict what you could do to make your weight go up or down on a scale? Part B, when you're standing on the scale, what can you do to change your reading? Now, obviously, you can go on and off, right? As you're going on, or if you have heavy things on you, you can remove them, right? They tell you to take off any heavy shoes, any heavy articles. If you have a backpack, take it off because they want to measure your weight, right? So removing those extra things makes it so there's more of your weight. But then they tell you to stand still. What does that got to do with your weight? Or does it? And you know that if you kind of like move up and down like rapidly, don't jump on and off the scale, okay? But if you're on a scale and you just like kind of bob up and down fast, like you fluctuate, you go back, you bob up, bob down, bob up, up, bob down, you'll start seeing that the numbers change. And then from there, you can predict, okay, if I bob up, what happens to my reading on the scale? If I bob down really quickly, what happens to my reading on the scale? Spoiler alert, a bathroom scale does not measure your weight. Repeat, it does not measure your weight. And you know that because if you tried the bathroom scale thing, you realize that you could fluctuate the numbers. You could actually work the system. And believe it or not, it depends on where you take your measurement. So, for example, if you were to weigh yourself on the beach at Santa Monica, you would weigh a certain number. Okay, and if we instantly flew you like a second later with the same bathroom scale to Colorado, Denver, Colorado, which is a mile high, you'll recognize that your weight is actually slightly less. And then if we go ahead and instantly transport you to the Himalaya mountains, right, to Mount Everest, the tallest peak on the Earth's surface, you would recognize that even more so that your weight would be a slightly even more or less than it was at the beach. So obviously, location also has to do with your weight. But your weight didn't really change, did it? Or did it? Well, the bathroom scale does not measure your weight. It measures something called the normal force. Okay, and there's nothing normal about this. Normal is another word for perpendicular, like you have in geometry. Perpendicular forms right angles, okay, forms 90-degree angles. The basic idea here is that the normal force is perpendicular to the surface. In this case, the bathroom scale, right? You stand up straight. If you didn't stand up straight, then your weight would be different. And it's not because your weight is different, it's actually because the bathroom scale is measuring your normal force. And you can actually mess with the normal force. So that's when you bob up and down quickly and change directions, bobbing up and down on the bathroom scale, you realize that the numbers are changing. And it's because your normal force is changing. Here's a blog just sitting there. Imagine yourself right now sitting watching this. Okay. You have a weight going down. Let's say, just for kicks, let's say it's 30 newtons. You're not falling through the earth. You're not falling through the ground. You're just sitting there, which means the earth must be pushing back up with a force of 30 newtons to keep you from falling through the earth. There's other things, other factors too, right? Like surface density and surface tension and and the other things, but don't worry about that.
That's all there is to it.
Right? Newton's third law says that for every action, there's an opposite and equal reaction. So if the weight's going down at 30, that means the normal force, which is usually with a lowercase n, the normal force is going to be equal to 30 newtons going up, right? It's equal and opposite. That's why you are sitting where you are and you're not falling through or falling up or anything like that. That's a very basic one. Let's say this is 30 newtons again, but we're going to put another block on top of it, which has a weight of 10 newtons. What is the normal force going to be of the larger object?
Most impressive.
The normal force is the opposite and equal reaction. So if I have a total of 40 newtons going down, that means I had to have 40 newtons equal but opposite in the other direction, 4 newtons of force going up. So in this case, the normal force can be made heavier if we go ahead and have extra things on us, or if somebody were to come along and push on us, right? So if we were standing on the bathroom scale and somebody came along and pushed down on our shoulder, all of a sudden our quote unquote weight reading on the scale would be larger. And it isn't so much because of our mass or our weight, it's because the normal force changed. You collect all the down forces and it'll end up being your normal force going upward. So again, the weight is 30 newtons. This rope, you'll notice this rope has some tension going up, but it hasn't quite lifted the block off of the ground. It's helping to alleviate some of it. So it's helping to remove some of that tension. Okay. So let's say this rope is pulling up with 10 newtons. This now becomes an issue with third and first law. So they tend to work hand in hand with each other. So if I have 30 going down and I have 10 going up, my normal force is going to be only 20 newtons. How come? You might want to left column this idea, but notice we're keeping things balanced according to Newton's first law. You have 30 going down and you have a total of 30 going up. And then finally, this last one gets pretty fascinating. Let's propose to you that this object weighs 30 newtons. However, you have the rope that pulls up at 10 newtons, and on top of that, now you have a spring that's also pushing it up at 10 newtons. So think for a moment, imagine if you will, that you're standing on a bathroom scale and then somebody, let's say a younger sibling comes from behind and tries to pick you up. They obviously don't pick you up enough to remove you from the bathroom scale, but they are helping to remove some of that weight, right? Quote unquote, some of that weight. So the bathroom scale will actually read that you're lighter, even though you're still touching the bathroom scale. It's because somebody came from, below or from somewhere else, and they went ahead and pushed upwards so that it's changing the dynamics of the system. Notice what's happening here. We have 30 going down, we have 20 going up, which means our normal force has to be 10 because we need 10 more to make this thing be in equilibrium and be balanced. So the normal force in this case would only be 10 newtons. Notice that you have 10 going up of normal, 10 going up for the tension, 10 going up from this force that's being pushed upward by the spring. That's a total of 30 newtons, and that is opposite and equal to the 30 newtons going downward. Now, in these cases, we decreased the normal force, while in this case, we increased the normal force. And in the regular cases, the weight is the normal force. A 10 Newton box means this is the weight. So if 10 newtons are going down, what must the normal force be going up? 10 newtons sounds good. Okay, it's the same as the weight. Part B though, look at this. This was Newton, so that's weight. This is kilograms, that's mass. We're gonna talk about this a lot more in detail later. Okay, however, we said that weight depends on gravity. Okay, it's a mass that's being multiplied by a gravity. So if I went ahead and if I took the 10 kilogram mass and I multiplied it by Earth's gravity, which we'll tell you more about later. I just want to kind of give you a sneak peek. That's going to go ahead and give you 98 newtons. Now, 98 newtons is the weight. But just like in part A, if this box is at rest and there's nothing else acting on it, the weight is the normal. So therefore, the normal is 98 newtons. A 10 Newton box rests on a spring that pushes it up on it with 2 newtons. The book is not moving. So what we have here is we have a spring. The spring is pushing up with 10 newtons, but the thing weighs, 2 newtons, but the thing weighs 10 newtons. So we have 10 going down, 2 going up. That means the normal force must be equal to 8 newtons to keep it balanced, right? If we want to make sure it is not moving, and we keep it in first law in equilibrium, then in order to keep this balance, we have to have opposite and equal reactions. Finally, we have a 5 Newton book that rests on top of a 10 Newton box, which rests on a table. So we have the box, weighs 10 newtons, which means the normal force is 10, but there's a book on top of the box. That's like pushing down on the box. So that means the normal force is going to be the sum of both of those, and we end up getting 15 newtons for the normal force for part B. For problem 6, I want to draw you 2 extreme examples, one very plain and the other one a lot more advanced. Because this is an algebra-based physics class, we will not be doing the trigonometry that goes with this. Those of you interested can reach out to me, and I'll give you that opportunity to learn how to do that stuff. But it suffices that we go ahead and show you just by way of introduction what some of these things look like. So here we have 2 examples. One of them is going to be on a flat surface. And what happens is if we have a weight going down the normal force is going up. Remember, it's called a normal force because it's perpendicular, right? It forms a right angle with the surface, even though that was a bad surface. For a second example, make sure you draw this carefully. We're going to draw a triangle. I'm going to put the box on this surface. Notice that this top is parallel to the ramp. Okay, make sure you draw it like that. You might have to go ahead and maybe turn your page a bit so you can see what's going on. We always draw the forces from the belly button, right? The normal force must be perpendicular, so I'm going to draw it straight up. Let's try that again. I'm going to draw it straight up, and it forms a right angle with the surface. However, the weight always goes straight down. So what happens is that you'll notice that there's an angle. Remember, the weight always goes straight down. No matter how you turn it, weight is always straight down because it's directed towards the core of the larger object that's exerting a gravitational pull on it. The normal force must always be perpendicular to the surface. For your summary, what can be done to change the normal force? Take a few sentences to go ahead and explain that.